Again, I'm Neal Bolger, part of the organizing committee and working group 3, and we're going to start off our first power talk from Big Ladder Software. We have Nathan Oliver, who I will invite to the stage to share a bit about adapting to climate change. So.
All right, so I'm Nathan Oliver. I'm from Big Ladder Software, and today I'll go ahead and talk to you about adapting to climate change, new weather files for warming California, more specifically, new proposed weather files for Title 24, 2028. So in energy modeling simulations, the ultimate goal is to closely match the building and weather to reality. But one problem has been that the weather files have been based on historical data, but the climate is getting warmer, and historic data is generally colder than what the building will experience. So you might end up underestimating the cooling load and overestimating the heating load. So one way to solve this problem is, instead of using historical data, is to use future weather data to create weather files. So you might ask, where can we get future weather data? So there's one organization called CalBEM, which creates future weather data based on global climate models. So there are several different climate scenarios can be selected. Each scenario is called an SSP, also known as a shared socioeconomic pathway. The differences in each scenario differ on how well countries work together to fight climate change, each varying by the amount of warming in the future. The CEC has decided to use SSP 3-7.0, also known as the business as usual scenario. And the years 2030 to 2059 were selected because this is the year range used for life cycle analysis of new buildings. But before getting into using future weather data, let's go ahead and talk about how to create a weather file. So to create weather files, a common process is to use the TMY process. So each month in a TMY represents typical weather conditions from one specific year, chosen from a range of historical years. In this example, I'll go ahead and talk about the years 2001 to 2011. So several weather variables are considered and weighted, such as solar radiation and wind speed, to select the typical year for a month. So how is a typical year selected to represent each month? So for this example, I'll go ahead and discuss how January 2005 is selected to represent January in the weather file. So as mentioned earlier, several weather variables are evaluated to select January 2005 for January. In this example, we'll only look at daily average dry bulb temperatures for January. Here we have a distribution of temperatures for January, so all the Januaries between 2001 and 2011. So here in gray, we have all of the individual Januaries, some being hotter, some colder. So this could be the year 2001, this could be the year 2010. So the year that most closely matches the historical distribution, the dark blue line, is selected as the year for the TMY. And that's if the daily average dry bulb temperature is the only weather variable considered. We will use a similar TMY process to create weather files using future weather data. So the red line represents climate model data for a future year range, here 2030 to 2059, but we cannot use this data directly. We need to first compare the model data and the observed data over the same historic time period. Ideally, these two distributions would match, but they do not. We have to make some adjustments to correct for that bias in the model data before using it. Shown here is a simplified process to bias correct the data. The difference between the distributions is calculated as shown by the red arrow here. This bias correction is then applied to the future model data, as shown here. After applying the bias, we have our future bias corrected data. So compared to the historical observed data, it generally has higher dry bulb temperatures. The TMY process is still used to select the typical years, but the closest historical year to the future bias-corrected distribution is selected. And so we still use historical years to create the weather file. The selected year here is highlighted in dark red. Here is a comparison of the year selected using the current process in dark blue versus the new future weather process here in dark red. This process is repeated for all months and all weather variables. The year selected here in dark red is not necessarily the year selected for the future weather file due to the weightings of other weather variables. So the year 2005 was selected for January based on the weightings of several weather variables. For California, we need to also use statewide coincident weather data for long-term system costs LSC analysis. So the final statewide selection is based on population weights of each climate zone. So how will the new future weather files impact simulations? So in general, cooling energy use will be higher in each climate zone as shown here in orange. And so thank you very much. If you have any questions about this, as you might, you can go ahead and bug me afterwards. So thank you very much. Yeah.
Thanks, Nathan. All right, I'm going to invite Rob Guglielmetti up from NORESCO, who's going to share a bit about CBECC software project management enhancements. So, thanks, Rob.
Hey, everybody. Yeah, I'm Rob Guglielmetti with NORESCO, and been doing a lot with managing the CBECC, formerly known as CBECC, now just called CBECC project. And we're in the process of basically just migrating the source code, the CBECC source code, from one repository system to another. So let's see, there we go. Yeah, so basically that's what's happening in a nutshell, is that we're just moving. CBECC has historically, the CBECC source code has historically lived in an SVN repository on SourceForge, and we're basically just taking the whole thing and migrating it over to Git and putting it all on a GitHub repository, and trying to take advantage of a lot of the tools and the systems and workflows that are available to us by making such a change. Man, this text is like really small. Let's see. Can you see? I'm like looking through the very bottom of my lenses, you know. So yeah, I mean that's the main thing. I mean, currently this is where CBECC resides. We already have I'll get to this in more detail in a second, but we've already sort of done a test migration of all of that. So source code, commits, history, comments, tickets, all those kinds of things you know, we've already migrated everything over to a GitHub, like a sort of a test repo. And we actually have it all synchronized right now so that the developers can continue doing their work on the tools that they already know. And we're behind the scenes, we're just sort of like synchronizing what's happening in real time with the live site with this sort of testbed GitHub repo while we build out some of the rest of the functionality. You know, why are we doing this? I mean, to me, you know, the fundamental piece of this is that CBECC is open source software, right? And you know, a core tenet of that is that it's freely available, it's transparent, that there's transparency in the entire process, the development process, the code itself, how it's developed and how it's delivered and how it's shared and how it's documented. All those things are like really foundational to the notion of open source software. And so we're using what has sort of become the de facto you know, home and repository and toolkit for open source software projects, which is Git and GitHub. So that's the main thing. Ultimately, the long and short of it is that we hope that this will really help the team, the core developer team, to do their jobs better, give them more opportunities to do things like beta testing and you know, ticketing a different way, and even just doing software builds a different way and releases and all those kinds of things. And just really like kind of centralizing, hopefully, the way CBECC is delivered and supported to the public, right? So that, like, you know, this GitHub repository could be your one-stop shop for looking at the source code, looking at you know, the development process, roadmaps, and getting releases and getting access to documentation. So yeah, what are the benefits? I already said all that. So yeah, some of the other stuff too is just, as I mentioned earlier, like taking advantage, the hope is that we can take advantage of some of the other things that GitHub has sort of risen up to support, and that's the notion of like continuous integration and continuous delivery, which are like software concepts, software, developer, project management concepts around. Foundational to that is testing, continuous testing, and continuous delivery just sort of suggests the notion of more frequent builds available for testing, and like sort of beta testing, and documentation. This could be potentially a place, an alternative place for the ACM, or again, like beta testing or closed, preview testing. And yeah, so I just said all this. I keep doing that. And yeah, just real quick, so what's the progress? So the migration is in progress. As I said, there's already a test site set up, and we're just building out the rest of what the site looks like, best practices, how to do commits, how to do releases, and the goal is to have the developers working on that site live by the end of this year, and so that there's been 6 months of working with the new system before the first 2025 release is out. Thanks. I'm out of time.
Awesome. Thanks, Rob. All right, I'll invite Neal Kruis, also from Big Ladder Software, up to talk about demystifying heat pump performance data.
All right, thanks, Neal. All right, so we know heat pumps are getting a lot of attention, and they're seen as a key technology in solving the global climate crisis. And we're going to continue to see big pushes for heat pump deployment moving forward. But what do we actually know about how modern heat pumps perform? It turns out not much. AHRI gives us heating capacity at 2 outdoor temperatures, at 47 and 17 degrees. And these are at what AHRI calls the full load conditions. The only other information we get is the heating seasonal performance factor, or HSPF2, which really doesn't help us much, and I want to explain why that is. The HSPF2 is calculated using these 2 points that you see here, along with several other test points that AHRI never publishes. AHRI then plays connect the dots to make up the rest of the story about how the heat pump performs. The HSPF also makes an assumption about the building load, represented by a straight line here. And anytime the load is below the minimum capacity of the heat pump, your system's going to be cycling on and off. Anytime the load is between minimum and maximum, your system will be modulating to meet that load. Anytime the load is above the maximum capacity, you're going to need backup resistance heat to meet the load. But the reality is neither the capacity nor the load are straight lines. Instead, the load is more of a cloud of points, where some hours are going to be cold and sunny with low load, and other hours are going to be warmer with no solar gains to offset the load. On top of that, there's this assumption built into the HSPF2 calculation about the weather. So this is the distribution of heating hours in different temperature bins, and you'll see that the assumption of HSPF2 is much colder than any of the climate zones represented in California. So HSPF2 really isn't appropriate for California. At the end of the day, these seasonal ratings are just oversimplified energy models of the wrong home and in the wrong climate. They aren't very useful when you're trying to do real energy modeling, which is why we need better data for heat pump performance. So fortunately, Northeast Energy Efficiency Partnerships has assembled this database of heat pump units that includes performance beyond the AHRI ratings. There are now almost 150,000 products in this list that meet their cold climate heat pump requirements, which includes that they have to be variable capacity and they have to have a COP of greater than 1.75 at 5 degrees Fahrenheit. The NEAP data contains the AHRI rating data highlighted in red here, but it also includes the capacity and efficiency at more speeds and temperatures. And so this gives us a much more complete picture of performance for heat pumps. But and with this data, with product-specific data, energy modelers can capture the more subtle technological distinctions among heat pump products. But on closer inspection, some of this data is obviously problematic. Each one of these dots represents one of those units in the database, and some of them have rated capacities higher than their maximum capacities. Some of them we found that have COPs greater than Carnot efficiency. And we've worked with NEAP to build in some much more comprehensive quality control checks, but it'll take some time for them to implement those. In the meantime, we kind of decided we couldn't rely on this data to use individual NEAP records. But there's still good and useful data here that we can use to inform better modeling approaches. So at the time we started working with this database, there were 125,000 units. And we started filtering out units. So there's a number of units that are inactive. They're not sold anymore. A number that are duplicates. There's same manufacturer will sell the same unit under different brands. And then there were a lot that didn't meet like physically possible criteria. We added some filters, some statistical filters. And at the end of the day, we had about 3,400 units that we could still use, which is still a decent sample size, nothing compared to 125,000. So how can we use that data to inform the new model? So if we start with the rating data from AHRI, we can look at, and if we say the 47 rated point, we want to figure out what the maximum point is, we can look at the distribution of that ratio. So a lot of units are rated at maximum capacity. A lot of them are rated at a lower capacity. And manufacturers can choose what speed they want to rate their equipment at. So we use this, the average value here, this dotted line, to inform that model. And then we do the same thing to find the minimum capacity. We look at the distribution of the statistical set of data, use the average value to figure out what is that capacity ratio. And we use these ratios to fill out the rest of this whole map. And at the end of the day, there's one last step where we have to decide which COPs to assign to these points so that if you were to use this model to synthesize the AHRI testing rating, then you would arrive at the same HSPF2 that the equipment is rated at. The goal is to get this approach added to the Title 24, a future version of Title 24, and the ResNet 301 standard. So that's it.